is an electronic commutation method that's incredibly simple that Ludic Science did, and we're going to replicate Ludic Science's commutation in order to get this Newman motor to work. Now, the circuit that we're going to use is this one. Okay, so that's it connected up. Now, I haven't bothered soldering everything, I've just held it on with clips, and you'll notice I'm using a standard silicon diode, a 1N4007. This is just the diode action, it doesn't matter if it's an LED. And for the transistor, I've got a 2N3055, which is a power transistor, because I'm using bigger coils, but any NPN transistor will do that suits the voltage and ampage you're using, and any diode will do. So let's give it a little bit of power. And there she blows. The idea that we could make a brushless DC motor from two simple components, and to do that we used one coil as a drive coil and the other coil as a trigger coil. Now, this idea of trigger coils are quite common actually. They were used in flash cameras for the transformer to build up the battery to the voltage that the flash camera needed, which was 600 volts. And they're very often used in flyback circuits when you're running from DC. In order to run a transformer or a motor, what you need is a varying magnetic field. And of course, if we apply a DC current to a coil, what we get is a permanent magnetic field. So we need to be able to switch it off and on quite rapidly, so that magnetic field will grow and collapse as we switch it off and on. Now, when we switch on a DC current into a coil and it has a coil next to it, or it has an iron rod or a ferrite going through it, then we build the magnetic field. And that magnetic field is either in the air or concentrated in the rod. And if we put another coil around that, because the electric current is creating an electromagnet, building up a magnetic field, that magnetic field will then intersect with the secondary current, a secondary coil, and induce a current in that secondary coil. Now, we can use that pulse of current to drive a transistor. So if we put that pulse of current on the base of the transistor, when the pulse of current comes in, it turns the transistor on. We connect the first coil to the emitter and the collector of the transistor, then it can flow. So once it flows and builds up the magnetic field, then of course nothing will happen when the magnetic field is static, and so the current going to the base will die, will turn off, and that will collapse the field. And this happens very quickly. Effectively, you're using a self-resonant circuit to turn the base off and on, because the secondary coil that you've wound is acting as a switch driven by the first. And remember, these things lag 90 degrees behind on an inductor. And so effectively what this does is act as a self-regulating automatic switch to turn the current off and on in this coil. So this coil is acting at the base to turn that transistor off and on. It's why it's not self-starting. I have to give it a flip to turn it on for a moment to allow the current to flow in here. So this is non-self-starting. It needs a mechanical input to start that process. Once that process is running, then the motor will continue to turn. It will continue to turn in self-resonant mode. So I'm sure you're well aware of the Joule Thief. The Joule Thief is a circuit that swept the internet a few years ago because, well, it's quite remarkable in that it can draw the power out of a AA battery well below the voltage that is supposed to be dead and do things like light an LED, and it really captured people's imagination as a possibility for free energy. But it ran the gamut of the internet with 1,000 million replications, but it is in fact a circuit called a blocking oscillator. Now, the blocking oscillator, which looks like this, is in fact the same circuit that we just used as an electronic commutator in a DC motor. It was first patented in 1974 by Roger Andrews of Salem, USA. Nobody